So this isn't a proper test equipment teardown, but this is a bit of a preview of a bit of kit that I've just received in the post, and it's the Racal SA520 digital frequency meter. Now this thing was originally designed and sold in 1962, so it's nearly as old as I am. It's entirely made from discrete transistors. They're germanium and they're PNP. No integrated circuits, no chips in this thing, but it's a proper digital instrument from the early 1960s. It doesn't quite work, so once I've made the repairs to get it working properly, I'll do a full teardown and we'll have a good look at it. But just to give a bit of an idea of what it can do, it has a non-inline display. Now, we don't really have these displays anymore. When Nixie tubes were introduced, they were sold as inline displays because the row of digits was in a line across the instrument. Here we've got 10 light bulbs. They're actually incandescent light bulbs in a column. So when it wants to display, as you can see here, this 2, it's not lined up with the zeros. There's actually a 0 here that doesn't really show up on the video. It is just showing. So there are 4 digits, and if it's showing zeros, there'll be 1, 2, 3, 4, 0 across the bottom. If it's showing 5s, they'll be in the middle, and if it's showing 9s, they're at the top. So the number that you read out is all up and down, not in a line across the display. Lovely and simple to just put light bulbs on a 0 to 9 counter, and this is what this is. It's just 4 decimal 0 to 9 counters. But of course, as far as the ergonomics of reading it out, it's a little bit strange, something we're not used to these days. HP made a similar kind of frequency counter. This is the Racal one. It's only got 4 digits, but it has got a range switch over here, so you can switch ranges, and by using the times 10 and times 100 you can actually get 6 figures out of it. The manual explains how to do that. Over here you've got some settings for period, so it measures frequency or period. There's a test switch here that doesn't seem to do very much. Not quite sure what it's meant to do. It's made that 5 come up, and now it's saying 6. I'm not sure that's actually working properly. One to have a look at when we do a bit of repairs on this thing. But in operate mode, I've got it rigged up. A couple of wires here. It's only a low frequency thing, doesn't have a BNC plug. There we go. That's wired up to a signal generator, and the signal generator is set to 440 Hertz, which is of course the note A above middle C, which is the International Concert Tuning pitch, and it's come out spot on. It's saying 440 Hertz. Now this 2 is not meant to be lighting up, so there's something wrong with this one. That 2 shouldn't be there, but the 4 is coming up, and that 4 and that 0. Now if I just reach over and fiddle with the signal generator, the signal's coming from a fine old Hewlett-Packard instrument, which is a 4204, which is a switched frequency signal generator. So the signal coming out of that, I can change its frequency 1 digit at a time. So I can change the initial 4 of 440 into a 5 and get 540. There we go, 540. Matches up with the HP. It didn't when I first turned it on. It seems to have settled down a bit. I'm not quite sure which end of the setup is having to reach operating temperature, but the oscillator is an RC oscillator, resistor capacitor oscillator, not crystal controlled. This has got a crystal inside it. It's got a 100 kHz crystal inside it. Not bad actually for something from 1962, rigged up to a 1970s oscillator, and it's coming out spot on right. Let's see if we can make some other numbers show up. Not so good. Hang on. Oh no, there it is. Oh no. The oscillator's controls are a little bit flaky, but there we have 560. Let's try 660. Yep. I wonder if I could get it to go up a factor of 10 here and get to 6,000. Yes, that's the oscillator is set to 6.6 kilohertz, and we've lost the signal. Now it's set to 6.5 kilohertz, so we should be saying 6500, and it's saying 6493. You see that the 9 is way up at the top of the display there, and the 3 near the bottom. It's not far off. Certainly this digit is working, although the 0 isn't coming on anything like as strong as it should be. It's not a blown bulb, because it does light up a tiny bit. You can just see it. That 6 is working. Something's wrong here. That looks like we've got a transistor which is shorted, stuck on. I think we've got a reasonable chance of fixing this. Let's fiddle with that frequency some more. That's 4.5 kilohertz, so 4500. I'm getting 4497, 4498. It's not far off, and as I say, I don't know whether it's the oscillator which is slightly off or the frequency meter which is slightly off. But enough messing about looking at the thing with the cover on and working. Let's get the cover off and have a look inside. Now, what have we got in here? Let's just swing the camera up a little bit. And there we have that's a row of boards. So we've got it is on. I won't get too close to this. I think it's a 12-volt power supply inside here. These will be the regulator transistors. A couple of fuses here. The big transformer is in the side. Each of these boards with the gold transistors on is one of the bulb drivers, the lamp drivers. Each row of lamps, or column of lamps, is in a plastic housing. There are 2 spare bulbs in each column of bulbs. Now I don't know whether they've already been used by the previous owner of this thing. It's quite possible that my spare bulbs will have been used up. Over here is a crystal, so that's the main oscillator crystal, the time base of the whole thing. So this board is the oscillator board. We've got divider boards in here and counter boards. I don't quite know for sure exactly what the different functions are. Something to find out. I have got schematics. There's a website where you can download the schematic for this thing. As I say, it's all discrete transistors. There's not a chip in here. 1962 chips were available, but they were very, very expensive. They were sort of thing that went on the NASA Apollo missions and didn't end up in instruments that you could actually use in your lab. So this is all discrete transistors, and as it happens, these are GET882 PNP germanium transistors made in England. I think the whole thing is made in England. It's British design. These transistors are marked Newmarket, which is a town in East Anglia. and a company called Newmarket Semiconductor made transistors there in the 60s. So I think that's rather a nice bit of kit. I think my next move's got to be, of course, find out why this 2 is showing up when it shouldn't be. So it means that this board here needs to come out, and I've got a nasty suspicion that getting the boards out of this thing is going to be a bit of a nightmare. It looks like they should unplug, and on a modern circuit you'd simply take these screws out and lift the board out and fix it. I don't think that's the case in this particular instrument. I think at the bottom of this, what looks like a rack of boards, there's actually a bunch of wires soldered to the boards, and they're only going to come out if I desolder them. So that's a bit nasty. That's not really designed to be serviced. Compared to a valve circuit, which would have been contemporary with this, it's very much more reliable than a valve circuit. It doesn't need to have valves changed. So perhaps the original designers thought, well, we don't need to make it quite so serviceable as a valve circuit, and we can make it much smaller because of that. You can change the bulbs by taking the panel off. See, there's a screw here and a screw here, and also down the bottom of the display there's 2 more screws. So this plastic panel comes off, and then you can see the bulbs, and I suspect you can change the bulbs without taking it to bits, but I need to get that board out to find out why that 2 is stuck. So there we have it, the Racal SA520 4-digit digital frequency meter from 1962.